A farmer hired a psychologist, an engineer, and a physicist to take a look at his barn where he kept his cows. The psychologist suggested that the barn be painted in bright colors so that the cows would be happier and theoretically put out more milk. The engineer suggested building stalls so that the maximum amount of cows can be fit to maximize output. The physicist brought out a chalkboard, drew a circle, and said, "Suppose this circle is a cow." I don't know if you get that joke, but very often in science, we try to simplify things. In fact, in today's example, we could simplify it by drawing a big fat circle. Let's say that Calvin really loves wagons, all right? And he asked every single family member for one, and that was what he got for his Christmas wish. And every family member also got him a different mass for the cart itself, all right? Now, you would think that to solve these type of problems, you have to go off and create 10 equations with a bunch of unknowns. Don't worry, it's not going to be as bad as that. We can actually use the shortcut, draw a big fat circle around all the objects, and solve it. In fact, we can solve all of this stuff over here in just this PowerPoint, right down there. All right, let's get started. First off, add up all the masses together, and as long as all the masses are going the same direction and they all share the same coefficient of friction, we can use this shortcut. Okay, so they're all going the same direction, they all share the same coefficient of friction. If you add it all up together, it works out to 143 kilograms. That becomes our new free body diagram. So that's the circle. So suppose this circle, this rectangle, represents all the wagons. All the wagons are being pulled with a net force of 200 newtons towards the right. They all have to deal with the normal force, the force of gravity, and a total force of friction, which is, in this case over here, 10% of that of the normal force. All right. So let's start solving this problem. First thing we got to do is figure out what the force of friction is by finding out the normal force. In this case over here, the normal force will be equal to that of the force of gravity. So the force of gravity is equal to mg. So 143 kilograms times 9.81 will give us our normal force. Multiply that by mu k, in this case over here 10%, and it works out to 140.3 newtons. Okay. So far so good. Next, we deal with the x dimension. Fc subtract the force of friction is equal to ma. And remember, this is total ma. So since the total mass is 143 kilograms, then 143 times a is equal to the forward force of 200 newtons, the backward force of 140.3 newtons. And once you solve for a, booyah, in one PowerPoint slide, you can get to that answer. In fact, let's do another part as well. Let's determine the tension right over here. Now, you might think that you have to draw a free body diagram for all these objects over here, but don't forget, if they all are going the same direction and they all share the same coefficient of friction, why not just draw yet another circle? And that's what we're going to do. Okay, let's just clean this up a little bit. Okay, so with that new circle will represent 1 plus 1 plus 2 plus 3, which equals 7 kilograms. There's our free body diagram. One thing that you have to do a little bit extra is recalculate the force of friction again. All right, because this 140.3 newtons, that represents the force of friction for all of the carts. We only need to know the force of friction just for these last four, and that's why you have to go through that brief calculation again. So yes, Fn minus Fg is equal to 0 newtons, so Fn is equal to Fg. Mu k is equal to Fn, so force of friction is equal to mu k times mg. I know it's a mouthful. Please show all your work. All right, that way the reader knows how you arrive to that formula. Okay, and as you can see, the force of friction is less because you're only dealing with just those last few masses as opposed to everybody. We finish it off as we normally do. If we want to figure out what the tension is right over here, then tension subtract the force of friction is equal to ma. And we've already solved for a earlier on. Okay, so ma is equal to tension number 4 subtract the force of friction. So tension number 4 we don't know yet, but force of friction we can bring over to the other side. So the mass of 7 kilograms times the acceleration of 0.41 plus the force of friction will tell us what the value should be. And there you go. In one PowerPoint slide, we're able to find out the acceleration of the entire system as well as the tension right over here. Isn't that amazing? I hope you appreciate that joke now. It does work every now and then. Let's try out another example, right? Something that's completely different. Let's say that Calvin decides to hang off a string that's connected to a wagon, and Hobbs is holding on to that wagon. When Hobbs lets go of the wagon, we know that the system will accelerate like this. And the question is, what is the rate of acceleration in this particular setup? I guess I have to give you some information. Let's say that the wagon itself has a mass of 45 kilograms, and Calvin has a mass of 30 kilograms. All right. Yes, you have to draw two separate free body diagrams as they're not going in the same direction. So you have a free body diagram for the wagon itself and a free body diagram for Calvin. Another important thing that you have to consider to solve these problems properly is that you have to define the direction of positive acceleration. We know for sure that the wagon will accelerate this way. That's the positive direction of acceleration. And as for Calvin, downwards is the direction of positive acceleration. And that will actually define our coordinate system. So for the 45 kilogram mass, positive is towards the right. As for Calvin, downwards is positive. And this is the most important part about solving these problems. If by accident you define positive the wrong way, for example, what I've drawn right over here, this would be a case where, for example, the string was replaced with an elastic band, and the elastic band is shrinking so that the two objects come back together again. And that's not the case over here. One is falling and the other one is moving. All right. So for Calvin has to accelerate downwards. Otherwise, this problem is impossible to solve. And you will get the wrong answer. Okay. So that's the most important part, getting the right coordinate system. Once again, we know the wagon is moving towards the right, so towards the right will be defined as positive. Calvin will fall downwards, so for Calvin, his direction of positive is downwards. Okay. With that in mind, now we can start solving the rest of this. I just made this problem fairly straightforward. Let's pretend that there's no coefficient of friction, therefore we don't need to solve for the y dimension anymore. All right. We'll still draw in the free body diagram just to be grammatically correct. For example, the 45 kilogram mass has a normal force, has the force of gravity, and it's the tension on the rope that's allowing the 45 kilogram object to accelerate. As for Calvin, Calvin's accelerating downwards due to the gravity, and it's tension that's preventing him from falling at 9.81 meters per second squared. So that's one thing to keep in mind, all right? The final answer will not be 9.81. If you think about it logically, it should be less than 9.81 because the inertia of the wagon is slowing the system down. Okay, so let's go through and solve through this, and you'll see that the answer is less than 9.81. Okay, the 45 kilogram mass, F net y is equal to 0. We're done. In the horizontal dimension, tension is our mass times acceleration, and you could start off with that as your first statement. That's perfectly fine. Ma is equal to T. We sub the values in of what we know, which is really just the mass of the wagon, and now we have an equation with two unknowns. Oh well. Move on to the next object. Remember, for Calvin, positive is downwards. So Fg subtract tension is equal to Ma. That is super important, okay? If you flip that around by accident, you're not going to get to the right answer. Sub in the values that we know of. For example, Fg is equal to mg, which is the mass of Calvin times the gravitational field strength of 9.81, and the mass of Calvin we could solve for as well, or subbed in as well. You could leave the equation alone as is, or you can rearrange. The preference is up to you, but you know that at the end we need to sub one into the next. Okay. Now, if you leave it like this and you sub this in, don't forget about the minus sign. That's probably the most common mistake people make. And as I mentioned before, in your second last statement, you're always going to have a total mass times A is equal to the net force. All right. So you'll see in this case over here, this negative 45 kilograms times A, if you bring it over, it becomes positive. So you should have a subtotal of 75 kilograms. If you didn't, then that's where the mistake came into play. All right. Now you can see that the acceleration works out to 3.92 meters per second squared. Therefore, Calvin accelerates downwards, not at 9.81 anymore, but at 3.9. And since the string remains the same exact length, that means the cart also accelerates at the same exact rate. Often in these questions over here, we're just looking for the magnitude of acceleration, so no, you don't really need to describe the direction. All right. But the question may also ask you, what is the tension in the string itself? And I hope you know how to get to that. Just sub this into equation 1 or 2, preference is up to you. Equation 1 will be faster. So you sub it in, And now you can find out the tension that's on the rope. All right. In fact, I want you to think about something. Will the tension of the rope be greater or less if this was a stationary system? In other words, let's say that Hobbs was just holding on to this. Would the tension be greater or less then? Okay. In a static system, you got to keep in mind that now the string has to hold him up so that he doesn't move at all. So the tension actually does increase. Okay. So the tension is actually less in this setup over here. So if he wants the system to work out properly, he can't just have a string with a strength of just 177 newtons as its max. That still won't be strong enough, right? Because at the beginning of the Tivi, it has to support his weight. Or it has to support 45 times 9.81, which is roughly around 450 newtons. That is something known as tensile strength, but that's a different topic for another day. Okay, so we'll leave it at that. And if you're sticking around for a bit longer, let's start working on the homework questions. Okay, so in this first problem over here, once again, if there's no friction, how about we just make life a whole lot easier by adding all of that together? So what does that equal up to? 15 plus 6, still 21 kilograms. So 21 kilograms is the circle that represents all of them. They're all being pulled with a force applied, which is equal to 42 newtons, just for our reference. We're going to take it that towards the right is positive and upwards to the sky is positive. We have our normal force and we have the force of gravity. Yes, you do need to draw that inside your free body diagram. No, do not draw the floor. Okay, that's not part of the free body diagram. Next, let's just work this out now. We know that F net in the x dimension is equal to ma. And ma in this case over here is just equal to the force applied, or 42 newtons. That's it. All right. And as for the mass itself, it's just 21 kilograms. Okay, therefore the acceleration is equal to 42 newtons over 21 kilograms, and that's equal to 2. 2 sig fig, final answer, 2 sig fig, 2.0 meters per second squared. All right, and what is the tension between the 3 and 4 kilogram mass? Well, that's not too bad. You could sit down and draw out a free body diagram for all three of them and slowly solve for that third tension, which takes a very long time to solve if you're inclined to doing that, let's say. All right, but as we may know, the super shortcut works as well. Group them all together. In fact, there's two different ways of solving it. You can either solve it by its tail end, or you can solve it by its front end. As for the tail end, since it's like the example that I talked about earlier, why not just rewind back on the video and see that shortcut? How about I just show you the other way of solving it, which will get you to the same answer anyways, all right? Which is, what if we grouped these guys together? So, staring at it, that works up to 15 kilograms. In the free body diagram, we have our normal force, we have the force of acceleration, force of gravity, and the tension that's holding that forward group back, all right? And remember, that tension over there would be the same as the tension on this side as well. So that's why it doesn't matter which way you solve it, you're going to get to the same answer. I'm just choosing the harder way because this is a homework take-up, all right? So why not? Don't forget to include a coordinate system so the reader knows what you're defining as upwards and forwards. Otherwise, they may confuse this as a bird's eye view of, let's say, north and east, all right? And in that case over there, the normal force and the force of gravity doesn't exist in that dimension. That means that gravity is dragging you aside, okay? It doesn't make any sense, all right? So yes, in this case over here, upwards is logical and towards the right is logical. We don't need to worry about the force of friction, so F net y is equal to 0. You can move on. If you really want to state that optionally, sure. Just to remind yourself, by all means. But as for your F net x, well then MA is equal to FA minus tension. Okay, so then the tension will be equal to FA minus MA. So 42 newtons minus the mass of 15 kilograms, and we've already calculated out the acceleration of 2.0 meters per second squared. So 42 subtract 30 would equal 12 newtons. In fact, that should be the case, where if the tension over here is 42 newtons, then the tension everywhere behind should be a lot less, all right? So the front train always has the greatest amount of stress on its link. It has to be able to pull all the other carriages behind it. Meanwhile, the last carriage doesn't have to bear much more weight than what it possesses. Okay, so you would expect the values to drop. So 12 newtons, that makes sense. All right, I think I have this all PowerPointed away, but that's okay. And this probably also shows you the other approach, all right, from the 6 kilogram mass, and you can see it gets you the same exact answer. What about this question over here? Well, this one's going to be a bit harder, because now we're going to say that, oh, actually, it's the other one that's even harder. This one's still doable, all right? They're all being pulled in the same direction, that's towards the right, and they all have the same coefficient of friction. So if that's the case, let's add them all up. That works out to 21 kilograms. They're all being pulled by FA. They all have a FN, FG, and they're all being pulled with a combined force, where the force is based upon a normal force, but the normal force is based upon the combined forces altogether. Okay, so the math will work itself out. Don't forget to include a coordinate system so the reader knows what you're defining as, upwards and towards the right. And since there's friction involved this time around, we do need to solve for our F net y, which is equal to Fn minus Fg. Just draw the strikeout to 0 so the reader knows that this equals 0. And this is how you prove that Fn is equal to mg. Yes, you need to show this. Just like how you need to show the reader that the force of friction is equal to mu k times Fn. And you can just draw an arrow. That's fine with me. Or if you really want to do 1 and 2, sub 1 into 2, you could. But an arrow should be sufficient. So the reader knows that you're subbing that in. So that's equal to mu k times mg. All right. So show this all the time as you're a novice grade 11 student. Okay. I suppose at some point in university, you don't need to show that anymore. But right now, while you're still in high school, show all your steps. Okay, so we could calculate this out. FF is equal to mu k of, we always like to use something nice and clean, 10%, so wax on wax, why not? 21 kilograms times 9.81 newtons per kilogram, and that will be equal to the same as 2.1 times 9.81, 20.601 newtons. Sure, we'll carry some extra sig fig. Not that it matters too much, because our final answer is only going to be 2 sig fig at the end anyways. All right. Okay, so next thing is our x dimension. So we know that our F net x is equal to ma, and that's equal to Fa subtract the force of friction. So our acceleration is going to be equal to the force applied of 42 newtons minus the force of friction of 20.601 newtons divided by the mass of 21 kilograms. So acceleration will be equal to 1.019 meters per second squared. That is our net acceleration. All right. What are we looking for? The tension at T5 and the tension at T2. Now, when it comes to test time, I'm going to physically tell you where they are, because right now this is rather ambiguous. I take it that tension 2 is over here. 3, 4, 5. This was probably what I implied about T5. Okay. You're doing the same thing as before, where I'm just going to do one of them right now. How about I just do the last two? Why not? Just as a reminder, you need to combine them together. So 1 plus 2 gives you 3.0 kilograms. All right. The normal force pulls it up. Force of gravity holds it down. Tension is what we're trying to solve for, but this also has its own corresponding force of friction. All right. So don't forget to state your F net y, which goes to 0, is equal to Fn minus Fg. So your Fn is equal to mg. Your force of friction is equal to mu k Fn, which is equal to 0.10 times mg, which is 3.0 kilograms times 9.81 newtons per kilogram. Whoops, times 0.3 will give you 2.943 newtons. So you have to recalculate that part out again. All right. And as for your F net x, your ma is equal to T2 minus the force of friction. So your T2 is equal to your mass of 3.0 kilograms times your acceleration of 1.019 meters per second squared minus your 2.943 newtons. Or is it add? Add, sorry. When you rearrange and you bring your force of friction over, it will become positive. Okay, so T2 is equal to ma plus the force of friction. So 3 plus 3 will give you your 6 newtons, which is probably what the answer is anyways. 6.0 newtons. All right. So this question over here, you want to pay attention to. All right, what if the 1 and 2 kilogram mass have a different coefficient of friction as compared to everybody else? What you going to do now? Well, unfortunately, you can't group them all together because they all don't share the same properties. Now you have to create 2 separate groups. But you already seen how to do that. It's not too bad with 2 separate groups. All right, so our first group works out to 3 kilograms. That's equal to our Fn, Fg, tension, force of friction, upwards and towards the right as positive. I'm just going to show you once and only once, and I'm just going to recycle this afterwards. F net y goes to 0, which is equal to Fn minus Fg. So therefore, Fn is equal to mg. We know that the force of friction is equal to mu k Fn. So if we sub this in, our force of friction is equal to mu k mg. So in this case over here, 0.4 times the mass of 3.0 kilograms times 9.81 newtons per kilogram will equal 11.772 newtons. Now we can move on to our F net in the x dimension, which is ma is equal to tension minus the force of friction, and that's a tension right over here, our T2. So therefore our T2 is equal to ma plus the force of friction. After all, the force of friction should induce more stress or more tension onto the rope. So our mass, we haven't figured out our acceleration yet, so we really can't do much here other than create the statement. T2 is equal to 3.0 kilograms times A plus 11.772 newtons. We move on to the second object, which 11, 12, 13, 18 kilograms. And that's due to our F of the hand. Subtract the force of friction. We have our normal force and our force of gravity. Our force of friction is equal to mu k mg. Yes, show all your work. That was a work shown before. This time around it's equal to 0.1 times the mass of 18 kilograms times 9.81 newtons per kilogram. .658 newtons. So our F net x in this case over here, ma, if I really want to call this m2a, sure. m2a is equal to the force of the hand, subtract the force of friction, subtract tension. So that's equal to 18 kilograms times A is equal to 42 newtons minus 17.658 newtons minus open bracket 3.0 kilograms times A plus 11.772 newtons. And the most common mistake people make is that even though they distribute the minus sign into the 3 kilograms, they completely forget to distribute it into the second term. So the second term also has to be negative. After all, when you look at the setup over here, you have a forward force of 42 newtons, and the friction should cause it not to accelerate as good. So it should decrease its ability to accelerate. So it should be a minus sign. I've also mentioned that when you state your F net is equal to ma, you're talking about the total mass. So when you bring the 3 kilograms over, it should work out to the total mass of 1 through 6 kilograms, which works out to 21 kilograms. newtons. Take that, divided by 21, and you'll see the acceleration is peanuts now. Is that enough sig fig? Ooh, that rounds up to us. Wait, 5986. That should be sufficient because, again, when you take a look at your givens, it's only 2 sig figs, so you don't need to carry more than 4, no more than 4 sig fig. It's completely unnecessary. All right, so that's the acceleration of the entire system, with the two sets having different forces of friction. So if we need to figure out what T2 is, then we can just sub it back into here. So T2 is equal to 3.0 kilograms times 0.5986 meters per second squared plus your 11.772 newtons. So yeah, sub A into equation 1 again. All right. That's equal to, let's go through this, 3 times your answer plus 11.772, which will give you 13.57. And if this was the end of the day, then we'd round that up to 14 newtons, and we're good to go for that part. Now, as for tension over here, it does get messier. Okay, many different ways of solving it. You could either have a free body diagram of T2 pulling to the left, 3 kilograms, and then T3, force of friction. That will totally work out. But there's also another valid solution, which is to group the front ones and work it through. Choice is up to you. Yeah, either way would have worked out, really. Okay, I'll just do it the harder way, and you guys can do the easier way afterwards. All right, just to prove to yourself you'll get the same answer. So in this case over here, we got to do the whole FF is equal to mu K mg in the first place. Okay, show all your work of why that's true. That's equal to 0.1 of the mass of 3.0 kilograms times 9.81 newtons per kilogram. .943 newtons. So in this case over here, for our F net x, this is T3 minus T2 minus the force of friction is equal to ma. So that's your net F net. Okay, so T3 that you're trying to solve for is equal to ma plus T2, which increases the tension of T3 if you think about it logically. Same as the force of friction. It should induce more stress onto the tension, because without those rear wagons and friction, there would have been less tension. Okay, so let's sub everything in. 3.0 kilograms times our acceleration of 0.5986 meters per second squared, plus our T2, which hopefully we didn't make any mistakes with that, of 13.57 newtons, plus our force of friction. Pull out your calculator, and 3 times 0.5986 plus 13.57 plus 2.943 would have been equal to 18.308, I think. Yeah, 18.31 newtons. Since our givens are just 2 sig fig, round it to 18 newtons. All done. And there you go. Once again, I would strongly recommend that you try out solving it from this perspective. All right, and you should get the same answer for T3. It's a great exercise. All right, this last machine, this is also known as an Atwell machine, made after a clergyman. His last name's Atwell. And he was trying to do an experiment to try to slow down the rate of acceleration. And if you've ever set up something like this, you know that they're not going to move as quickly as 9.81 meters per second squared. So you know your answer is going to be less than that. How would you solve this? Well, you have to think about it intuitively. What's happening over here? You're competing a 15 versus a 25 kilogram mass. Now, if they were the same, either they'll remain stationary, or if you give one a nudge, they'll move at a uniform rate. Remember the law of inertia, right? If the F nets are balanced, then it'll either remain stationary, or it'll just keep on constantly moving, one or the other. So in this case over here, we know that logically, the 25 kilogram mass being heavier, that will fall downwards. So that will be your positive direction of motion. As for the 15 kilogram mass, it's going to get pulled up. So here are free body diagrams. Once again, this is the most important part. If you make them both go up, the only way that could happen is if it was an elastic band that was already stretched and is trying to contract. All right, then sure, it will give an accurate result based upon that condition. But this isn't that case. This is a string that which will never stretch, never shrink. So it'll always remain the same length as one rises and the other one falls. All right, so for the first mass, M1A is equal to the positive direction of tension, subtract mg. As for the second object, it's mg subtract tension, which is equal to ma. Okay, so watch out for that. Aside from that, just sub everything in and slowly solve for it, and you'll get to your answer. All right. Now, it doesn't matter which one you isolate for t. Preference is up to you. And yeah, we'll go through this then. And tension is equal to 15 kilograms times A, and it might be easier just to combine that all together. So pull out your calculator. 15 times 9.81 will give you 147.15 newtons. Sub 1 into equation number 2. So you have 25 kilograms times A is equal to, let me just calculate that out. It's 25 times 9.81. 245.25 newtons minus 15 kilograms times A plus 147.15 newtons. Once again, watch out for your distributive property. Don't leave it as that, because that's going to be the wrong answer. That minus sign will go into both terms. When you bring the 15 over, you'll notice that your next line is always going to be this. All right, the subtotal of all the masses times A. If it's any less than the total mass, you know something went wrong and you're rearranging. All right, so you have a forward force, and then you have retaliating force. That's why your F net will be less. So 245.25 subtract 147.15 will be equal to 98.1 newtons. Divide that by the 40 kilograms, and now you have your acceleration. 3 sig fig, 3 sig fig. I think everything's 3 sig fig, so your acceleration will be equal to 2.46. I'll just write down the 2.4525 meters per second squared. Why? Just in case if you need to reuse it. You want to have that data available. All right, even though your final answer should just be 3 sig fig, I guess I accidentally wrote it down as 2 sig fig in the answer key. So 2.45 meters per second squared. It doesn't matter to me on the test if you accidentally do that. Since these are calculation-based problems and you're limited in time in answering it, I'm going to be fairly lenient on that. Okay. But when it comes to lab time, you have to be specific because you had time to work on it. Okay? You had a whole evening at least to sit down and look through it. What's the last thing? Find the tension on the string. So sub it in. So sub A into equation number 1, since that's easier. T is therefore equal to 15 kilograms times 2.4525 newtons plus, where's the minus? Yeah, no, plus 147.15 newtons. Good to go. Oh, this is a fun one. Okay, let's start off by drawing a free body diagram. Okay, the mass of the clown, you could probably figure it out by taking that and divide it by 9.81. Hopefully you can see why. All right, why the mass is equal to FW, or for the weight of the clown, divided by the gravitational field strength of 9.81. Do we really need that from here? Probably not, but if you want to calculate it on the side, you're more than welcome to. What do we know about this so far? Well, we know that the clown is being pulled up due to a tension that he's exerting on the string, but that string is also pulling on his legs towards the left. Now, if it was frictionless, he'd just be swinging around like crazy, but we're trying to figure out what the minimum pulling force is so that he can fight against this thing called friction. And friction always opposes the direction of travel. That's why you'll see that my left is my positive and my force of friction would be the negative. Don't forget that gravity still exists in this problem. Okay, so there is your free body diagram. Next, let's solve all the components. All right, your F net and your Y dimension. I'm so glad I turned this on. Otherwise I would have forgotten. The clown's on the ground, so the ground is exerting an upward force. All right, so that's why the Fn also needs to be in the free body diagram. Okay, so what's your F net Y? Well, your F net Y is tension plus Fn minus Fg. If we wanted to just glide, that means we want to make sure that our F net Y goes to 0. Therefore, our Fn will be equal to Fg minus tension. What is our Fg? Well, don't need to calculate our mg because we have our 890 newtons. So our normal force is equal to 890 newtons minus tension. As for our force of friction, that's equal to mu s times Fn. So our friction is equal to, do I have that power pointed out? I guess not. Yeah, it's okay. Let's go through this because I'm sure I'm just trying to simplify this into a problem. Okay, so that's equation number 1. Next, we deal with our F net in our x dimension. So tension minus the force of friction should be greater than 0. Right, because we want it to just accelerate. What is this telling us? This tells us that if this is greater than 0, then tension has to be greater than the force of friction. Okay, so if that's true, then tension has to be greater than your mu s times your Fg minus t. Now, you'll see that t is on both sides, so we have to clean it up. And the only way to clean that up is by distributing it. So mu k Fg minus mu k t. Bring this term over to the other side, so you have t plus mu kt is greater than mu k Fg. Factoring out our tension, so tension is equal to 1 plus mu k, which is greater than mu k Fg. And then lastly, our tension has to be greater than mu k times Fg all over 1 plus mu k. If you run out of space, then start a brand new column. So tension must be greater than mu k of what? Oh, static friction. Whoopsie daisy, mu s. Mu s, mu s, mu s, 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 s. There you go. So tension's greater than mu s, which is 0.53 times Fg, which again, that's why there was no point in calculating it out for your mass, because your mass times 9.81 will still give you 890 newtons. 1 over 0.53. Divided by open bracket 1 plus 0.53, or just divide by 1.53. That would have given us the same answer anyways. So our tension must be greater than 308.3 newtons. Okay, so greater than 308. So 309 would have done the job. Now you know. Keep on doing your homework. Catch you later. Or maybe not. One more problem. Okay, number 7. Okay, I'm not going to go through all these examples. How about I just do the last one? Why not? That's the hardest one of them all. Okay, remember that you have a cart and a mass on top, so you'll combine them together. So the cart has a mass of 1 kilogram, and the weight on top has a mass of 2 kilograms. That means for the free body diagram for the cart, that will be equal to 3.0 kilograms. Normal force, force of gravity in the y dimension, tension moves it forwards, but in this case over here, we have a coefficient of friction only for the cart, all right? As for the hanging mass, there is no coefficient of friction because it's just free falling, and we're not concerned about air friction in high school physics. So your F net y must go to 0 due to your normal force minus the force of gravity. So your normal force is equal to Fg, which is equal to mg. Force of friction is equal to mu k times Fn. So your force of friction is equal to mu k mg. Always show your work. Sub everything in. So 0.04. You may think it's nothing, but it does impact your answer. All right, I may see my answer key over here. So even with a 4% friction, you can see that the speed drops down to a little bit more than half the original value, but it's still quite significant, right? From 0.89 down to 0.54. But here we're trying to prove to you that it's going to be 0.54. So let's go through this. 0.04 times the mass of 3.0 kilograms times 9.81 newtons per kilogram. All right, so that's the force of friction. For our F net in the x dimension, we have tension, subtract the force of friction, that's our F net, is equal to m1a. So our tension is equal to 3.0 kilograms times a plus the force of friction of 1.1772 newtons. Okay, moving on to the second object. So we know the cart's going to move to the right. That's why I should have labeled this towards the right as positive. And as for the hanging mass of a value of 0.30 kilograms, Fg is the positive direction of travel. And it's the normal force that's preventing it from falling at 9.81 meters per second squared. So Fg minus your Fn, and if you really want to write it out as mg, you're more than welcome to. Mg minus Fn is equal to m2a, or m3. Not Fn, tension. Oopsie daisy. It's hanging. Don't forget, this hanging force is the tension. I won't write down positive because downward is positive. Okay, so tension is holding it up, but the force of gravity is pulling it down. Okay, so therefore tension is equal to 0.30 kilograms times A plus 0.30 kilograms times 9.81 newtons per kilogram. Equation number 2. We're going to sub 1 into equation number 2. Actually, I should have left it alone. Doesn't really matter how you do it. M3, 0.30 kilograms times 9.81 newtons per kilogram minus tension is equal to 0.30 kilograms times A. So this will be equal to 0.30 kilograms times 9.81 newtons per kilogram minus 3.0 kilograms times A plus 1.1772 newtons is equal to 0.30 kilograms times A. When you remove the brackets, this becomes minus. And let me just quickly get to the answer from here. So 0.3 times 9.81. Oh, now I got the answer. Okay, I don't know where my mistake came from. But yeah, that's what it should have worked out to. Okay, so acceleration is equal to 0.5359. No, 5351 meters per second squared if we need to reuse that number again. Okay, if not, 2 sig fig, final answer 2 sig fig. If you need to solve for the tension, sub that into there and solve it if you need it. Alright guys, that's it for today. Catch you guys later now, for real.